Share for you. We receive.
No, 1.33 is the speed of the electrons.
Right.
There's the speed of the electrons when they hit the target. Oh, you're right. Or they use a different value.
Yes.
Right. Okay, yeah, so that C, remember the E would have been the energy of the electrons. Okay? So this value here for C should have been this speed down here. Alright? So what would the value be? 1.1. No. Let's go back. This C will be speed of this C will be speed of this C will be the speed of the this C will be the speed of light. Alright, here's why. Here's why, right? Here's why. What was the answer? 2.4? Right, here's why. Because that V that we worked out here, alright, and then blue. Right? This speed that we worked out here is based on the energy that the electrons have, the speed they will move with. Right? This here, remember, was the assumption that we made for the X-rays to be produced, or the most energetic X-rays. And we assume all the energy transferred. So this E value here is the energy of the X-rays. Okay? So this energy of the X-rays, right, is equal to HC on lambda. Lambda is the wavelength of the X-ray, and C is the speed of the X-ray. All right? Okay with that? So the C is not the valued part. Okay? Okay with that? All right. So before I move on to radiation, there's one thing I left out. There's one thing I left out that I wanted to just run through quickly. Chemistry people would have seen this already. Yeah, Shiva, I can answer this. Oh wait, all right, let's go on here quickly. All right, watch this here. This here shows you, oh no, this is already value. Hold on, no, 1 second. I want to get one with the energy value. All right. I have one, no, I just not seen it on my list. Right, but here's I wanted to point out, right? If you look here, right? Let's say at the energy levels, right? What is called the lowest energy level, the ground state? What number is that? N equal to 1, N equal to 0. N equal to 0, right? So at N equal to 0, I don't remember the exact values earlier. Right?
So that's the color.
As well? Right? So basically, all of these here exist. Wait, you all seen 0 online? Well, this thing stick out here. Right, so those who online, don't use the whiteboard. Huh? Alright, I'm not sure why that happened, but I want to see it from here. Alright, so what's here? What's here? These are not the actual values, right? But for every energy level, every level, right? N is 0, N is 1, N is 2, N is 3. What's here now? Right? For each one of those energy levels, there is a specific energy attached to them. So for example, if an electron has, let's say, exactly 9 joules of energy, then it will go to N equal to 3. It can't exist anywhere else. This is an example of quantization, right? Electrons don't exist in the middle here. They must have a specific quantity of energy in order to exist at the energy level. Okay? Those bars on the left hand side are wrong, right? I'm sending back the picture I have. Right, but I'm not seeing it on the iPad. Right, but basically, those energy levels are the specific energy that the electron must have to exist there. So, in X-rays, we are talking about an electron being here, and then we're knocking it out. What will happen is the energy, an electron from a higher shell, maybe here, might come down and take its place. In moving down from N2 to N0, it's going to give off energy. Right? The energy will be the difference between here and here. So it might be like in my example here, 4 joules of energy. Right? And that energy given off is in the form of X-rays. Okay with that? So that's the principle behind line spectra, right? Right? These electrons could only exist at specific energy levels, right? And to move from one energy level to the next, you have to gain an exact amount of energy. For example, if you are at n equals to 0 and you gain 1 joule of energy, right? These are negative values actually in real life, right? Can you go up to 12? And the answer is no, right? Because if you're at minus 14 and you gain 1, that will take you to minus 13 joules, which is nowhere on the line spectrum. All right? So you have to gain exactly 2 joules of energy to jump from minus 14 to minus 12. All right? All right, Andy. Right? So you have to you have to get those exact energy levels to be able to exist, right? Right, just give me 1 more second. Let me just see if I can find it. I want to show you all the numbers.
Mama, I take the grace.
All right. I'll look quick.
I just think the down. Why?
All right. Let's go back. Anybody have 2001 number 7? No, you're not the only answer. I am. All right. I'll guess it because it's in there. It's in the line spectrum in there. All right. Let's run through radioactivity quickly. Well. Let's run through radioactivity quickly. Right? We would have done all these things already in Form 5, but I want to go through it again, right? Right, Jude? Follow what's up here, please. Right, radioactivity, the spontaneous decay of a radioactive element. 3 types, alpha, beta, and gamma. Alpha is a what? Alpha is a helium particle, beta is an electron, gamma is energy. Right, remember, you have to learn to balance equations. So, for example, right, if something undergoes alpha decay, it will lose a mass number 4, lose an atomic number 2. If it undergoes a beta decay, the mass number stays the same, but the atomic number increases by 1. If it undergoes gamma, what has happened? It ends up with the same particle, but with less energy. All right? Here's an example of uranium. Uranium lost 2 helium atoms, so 2 alpha and 3 beta. All you have to do is make sure the mass numbers add up for the reactants and products. That's okay? Alpha, beta, and gamma. Right. Here's the problem now. The problem now is in Form 5, we kind of knew that beta going down, alpha going up, gamma going straight through. But in a magnetic field, we have to be able to use the law and work it out. Which law is that? Which law will help us find the force? Fleming's left-hand rule. Right? Fleming's left-hand rule. Thumb is the force, first finger, magnetic field, middle finger is the current. Right, but remember, the current is the direction of a positive charge. Are you okay with that? So what does X mean again? In or out? X means in. So try there fast and see. Check and see if your thumb pointing upwards. So you feel into the paper, right? So the field going into the paper, your middle finger going from left to right, and your thumb naturally pointed upwards. How you will show the beta going down? How you will show the beta going down? Change the direction of the current, right? Take your finger, go in the opposite direction. Okay? So you're using Fleming's left-hand rule to work it out, right? So this is the force, this is the magnetic field. All right? So it's important to remember how to do those little things, right? Right? And well, oh, one last thing. Why the alpha particles traveling further out before it turn upwards? While the beta turning inwards faster. Why? Remember? Like. Which one heavier? Alpha or beta? Heavier? Alpha. Alpha is 4-2, right? Yeah. Right? So the alpha particle is much heavier. So it will take a longer while for the magnetic field to pull it out. Okay? Right? Next one. Right? This one easier, right? Alpha always goes towards the what? Negative or positive angle. And beta always goes towards the, and the gamma will go straight through. Right? These are your uses of radioactivity. Right? This is from Form 5. You gotta be able to do this. E is equal to mc squared. Right? You have to remember how to find the change in mass by subtracting them and then multiplying by the speed of light. Okay? Just one conversion. I think I have an example here. Oh yeah, we have one here. Watch this here, right? You have to add up the two products, add up the reactants. Remember you have a 2 in front here, right? And when you add it up, minus them. And then you have the change in mass. But remember, sometimes you just get the value in U. Right? And you have to multiply by 1.66 by 10 to the minus 27, right? Sometimes they might give it to you in atomic mass, right, Bara? And then you have to convert it to kilograms. And after you do it, multiply by the speed of light squared. Right? We'll do a passive another one. Huh? Yeah, we are it's the same thing, just a plug in the value. I'll do one as well. Right? And last thing we have to, well, not last thing, next thing we have to look at is something called binding energy per nucleon. Right? Binding energy per nucleon is basically the same energy you found on top divided by the nuclear number of protons and neutrons. Right? So when you find the energy, you divide it by a number, by the mass number, right? By a nucleon number. And when you divide it, you'll get a binding energy per nucleon. And the more stable the atom is, the larger that value. So, you all should have seen the graph already. That is the graph of binding energy per nucleon. Right? See on top here? Those are the most stable atoms because they have the highest binding energy per nucleon. Okay? The next thing you'll also recognize is that these small elements here, to enter up here, they undergo nuclear fusion. And these elements here, because they are large, they undergo nuclear fission to enter. All right? All right. And last thing I want to talk about, I want to go on the board and do it, half-life. All right? Let's take a look at what is half-life and then let's do some past papers on it. You'll see the whiteboard online? All right, ready? Let's see. Let's just take a look at half-life and a new quantity called activity. Right? It have a little bit of integration in this for non-math people. So in case they have to prove it, well, you shouldn't have to do. You didn't have the integration part, but I have the learn part to prove half-life. All right, so watch this here. Right? Activity. So the activity of a substance, the activity of a substance measures the rate of decay. Right? So the activity is the rate of change of decay with time. All right? And it could also be written as activity is equal to minus lambda. Right? A is activity. Lambda is something called a decay constant. Right? It gives us a probability of a particular radioactive element K, okay, in a particular time. So A is equal to minus lambda n. So this relationship here, right, helps us to calculate activity. Right? If you want to get initial activity, which is A naught, yeah, minus because it's decaying. Right? If you want to get the initial activity, right, that's A naught, then we need N naught. Right? N is the number of nuclei. Right? Number of nuclei present. So to get A naught, right? To get A naught is equal to minus lambda N naught. Right? And for those of us who did half-life already and remember a little bit, you should remember the shape of this graph. What's the shape of the activity with time graph?
It's an exponential.
Right, it's an exponential curve. Right? So therefore, A can be represented by exponential formula. Right? And it's represented by A is equal to A naught E to the minus lambda T. All right? We had to be able to prove the N version of it. All right? So, right, I'll do a little bit of integration here. Right? And you will get dN dt is equal. I using A is equal to this. Right? So I using dN dt is equal to minus lambda n. All right? Bring across dt, bring across the n. I will get 1 on n dn is equal to minus lambda dt. I'm going to integrate here. What's the integral of 1 on n? The integral of 1 on n is ln n, right? What's the integral of minus lambda? Lambda is a constant. The integral of minus lambda will be minus lambda t plus c. Okay with that? Right? From this, I can move across the ln, and I'll get n is equal to e to the minus lambda t, plus c. I can bring this up a little bit, and I will get n is equal to e to the minus lambda t dot e to the c. And if we let e to the c equal to the constant n naught, we'll get n is equal to n naught e to the minus lambda t. All right? So we had to be able to integrate, then make n the subject of the formula, and then replace this. Remember, this is a constant, right? We can call this constant n naught. And we end up with same formula basically. Right? And you can go from here to here if you want to. You could say n is equal to e on lambda and substitute it out. All right? So when you reach here, what is formula saying? This formula saying that after a period of time with a known decay constant and the original number of nuclei, we can work out the number of nuclei present. All right. So that's the way to prove it, right? And then let's talk about half-life. Then let's talk about half-life. Right on. This one.
Of course.
Think about how to get half-life from this formula. Right here. So the symbol I'm using for half-life is when t is equal to 1 on 2. Anybody can tell me when it's half-life, this value is how much? Half of this, right? So when this is half-life, this value n is equal to n naught on 2. So if I make a substitution here and here, I'll end up with n naught on 2 is equal to n naught e to the minus lambda by the half-life. Right? Because they cancel off the n naughts, and you'll get half is equal to minus e lambda t on 2. Then half-life. Still have 6. What is the next? No, we gotta make half-life with subject to the formula. Take ln here, take ln here. Ln of a half is minus ln on 2. Ln you'll cancel off and you'll get minus lambda by a half-life. And then you're moving lambda on this side. So you'll end up with half-life is equal to ln 2 on lambda. What's that? How come this is that? Ln 1 is 0. Ln 1 minus ln 2. Ln 1 is 0. Why is this? Right? So you have to be able to take this and be able to prove half-life. This came already. I can't remember if this before. Right? But this came already where they asked you to take this and prove this. Right? So you gotta remember, not much people remember ln. All right? So this is the remaining theory in this module. Let's take a look at some questions on this and the I want to show you the energy spectrum question as well. It's in the handout there. I don't want to show you. It's in the handout.
Why ETC is that?
Why E to the C is and no, but that is the constant. That's what I do. So E to the C is a constant value. And I said that constant value, that constant value is equivalent to n. Remember n not was the constant. So I equate it like that. That's how it based on what's happening, right? You want to see it. All right, so let's take a look at June 20 part C. Huh? Yeah, take it away. Let's take a look at this part C. Ignore part A and B. Let's jump straight to part C. Take a little read and it's going to get charged. Take a little read, let's figure it out. Who's that? Who's that from where? All right, so they gave us the mass, they gave us the atom, and they gave us the half-life. Right? They want us to find the number of nuclei. So how do we get number of nuclei present if you have the mass? Yeah. Remember, 1 mole has how many nuclei? I think we use 6.02, right?
Say 6.02 by 10.
Right? 6.02 by 10 to the 23. So for every mole, that's the amount of particles. Right? How we get the amount in 3.5 micrograms?
Where is it?
No. Yeah. Hurry up, Shabara. We need some help. We need some help. Yeah, Shabara, how are we doing that? How are we doing that? So remember, take the mass number. Take the mass number, right? 11 grams is 1 mole. Right? That's the RMF. Yeah. Right? 11 grams equal 1 mole. So it means that 3.5 by 10 to the minus 6 grams is how much? You find for 1 first, which is 1 on 11, and then you multiply it by 3.5 by 10 to the minus 6. That would be the number of moles present. You'll see now,
Yeah.
how much is that? 1 on 11 by 3.5 by 10 to the minus 6. 3.18 by 10 to the what? Minus 7 moles. All right? 3.18. That is your RMM. Okay? That's the RMM, right? So you take your RMM and you divide it by the mass and you get a number of moles. All right? Now to get number of nuclei, just multiply 3.18 by 10 to the minus 7 by 6.02 by 10 to the 23. How much nuclei is that? That 1.9. So 7. So that's the number of nuclei. That's okay? All right. So based on what we have there, just remember this, right? For non-chemistry people, remember just take the mass number and divide it by its mass. Take the mass number, it's 11, by the mass of the substance, and that will give you the number of moles. All right. Once you have the number of moles, multiply it by Avogadro constant. Take the mass number of the RMM and divide it by the mass of the substance. That will give you the number of moles. And there was a little triangle, so I will do it. Right. How we getting? Look at there. Look, I wrote it there for you and just give it to you. 6.02. Right there. Get it? Right. Question, Andy. Andy, they asked us to find decay constant. How are we doing that? Very good. So lambda is equal to ln 2 half-life. But half-life must be in what? Seconds. Right? Must be in seconds. So it will be ln 2 over how much seconds is that? 20.4 by 60 is how much? Much? 1,200. Right? So that'll give you your decay constant. Hey, you know, what's the answer for that? What is 5.66 by 10 to the minus 4. S, right? Sorry, S to the minus 4. Next question, Ruel. Ruel, how are we doing part 3, activity? How are we finding activity? We just found decay constant. Oh, sorry, they want a t equal to 0. So what are you asking for specifically? Huh? Which is what? A naught, right? How do you find A naught? Lambda by n naught. The minus sign just shows that decaying process, right? So you don't have to include the minus sign. It just shows that it's a decaying process. Right? Lambda is how much? Lambda is 5.66 What is N naught? Sorry? Yeah, that's what we found in part 1. 1.91 by 10 to the 7th. Alright, that'll be A naught. How you doing part 4, Adam? How you doing part 4? Find the activity after 8 hours. What we use it? Activity after time to check and see which formula of activity and time. A is equals A naught E to the right. E naught is how much? Oh, we just find part 3. When I wasn't paying attention, we will go part. And T is in what? T is in seconds. Good. Somewhere again up this. Now forget, yeah, but when you get A naught. Density 40. Oh, I forgot to mention. What's the SI unit? Sorry about that. The SI unit is what? Becquerel. BQ. Becquerel. It can also be disintegrations per second. Right? But Becquerel. BQ. I've never heard that before? Oh, yeah, actually right. We'll go part 4. Online, you're with myself, for those who are there. Amanda. Right, so we'll go to A value there.
Nine by 10. I think it is 6.
9 by 10 to the
6.
right? Sometimes you could kind of guess how many half-lives went there. How many half-lives went in 8 hours? A few, right? Right, so you recognize that the activity dropped a lot, right? It went from 10 to the 14 to 10 to the 6. Right? Let's go again. Any questions online? Karina, Shivani? Right, so except for plotting the graph, this is generally how these formulas come, right? Once they ask you to linearize that formula as well, and they plot blondie against, they remember how to linearize. All right, let's go. Next one. What? Try this fast and quick multiple choice. See this one? They want the mass equivalent in kilograms. So the mass equivalent of cubes. But they asked me to find Kishab. What they ask me is to find in part 2. Sorry, and first multiple choice. And they want the mass equivalent of Q. This all your values in UF. What they asking for there? They want the mass equivalent of Q. What do you do? When you have done all you can. Huh?
You is again 1.66, right?
10 to the minus 27. But which one you got multiplied by that value? Well, no, you gotta do something first. You want the mass of this, right? So, how you get the mass of that? Right? Take the mass of lead. No, sorry, not lead. What's PO? What's PO? Anyway, take the mass of PO. Take the mass of PO and minus helium and lead. And you will get you some value in you. And then you convert that to kilogram. So what do you get for you? I think you first. Set them away again. You. Christopher got 0.009. Yes, sir. Yeah, 0.009. 2 zeros or 3. And multiply it by 1.66. Minus 27.
1.4.
Couple.
Yeah.
Couple. Mass of the product, yeah, minus 20 mass of the reactant. And you get take this and minus these two masses. With those values. Yeah. And now I'll give you this. Then convert to kilogram. Bye-bye. Next one. What's lambda? Let's see. Right, lambda is the K constant, right?
Yeah.
Next one. How do you do with that? Look at the unit. How you find binding energy per nucleon again? How you find binding energy per nucleon? I told you a little while ago. It's the energy divided by the nucleon number. Find the energy. What's the formula to find the energy? Andy. How you going to find the energy? Yeah. Is equal to what? QV? No. Is equal to MC squared.
I say it again, correct.
Let's say M. Right? So use it is equal to MC squared and divide by nuclear number. But the problem is what? You have to convert to check current downstairs. Just have one. I don't know, right? It has to be in mega electron volts, so you have to convert the joules to electron volts, then to mega. Very quick. Right? How much you got in joules? When you multiply the mass defect by the speed of light squared. How much you got in joules? Right, all together. Second time we get joules first, right? And then we convert to mega electron volts. And that's physics next week. How much you get in joules? Right? That's the value in joules, and then you have to convert it to electron volts. 1.6 by 10 to the minus 19. That'll give you the value in electron volts and then convert to mega. Although there's a conversion for 1 mega in front. How much you get here? How much you get here? 0.07. 7.07 by 10 to the 6. Minus and positive. 1.13 by 10 to the minus 12 divided by 1.6 to the minus 19. Yeah. That'll be minus, that'll be positive.
Again, 7.06 by 26.
Right? That's electron volts. So that's approximately equal to 7 mega electron volts. See? So you get 20. Divide by 4. Because it's binding energy per nucleon. It was divided by 4. I know, yeah. All right, are you alive? Last one. Last one here. It's already. Okay, second, the last one. Find the decay constant fast. Right? Do you have to convert? Do you have to convert? You have to convert already in years, right? How much? Apple? All right, nice. Last one. Oh wait, it's just like the last one, so you shouldn't take long.
The last one was the last one.
All right, second, the last one. Apple. A. You got A there? On a calculator. Wait, say A. Oh, I thought you get A. Thought you get A on a calculator. All right, next one here, Andy. Close them out now. To this one. To this one, please, Andy. Last question. Right, actually, I just going up the first part so you can see everything, right? They gave you the original. Why are you looking like the same thing? Same mass, eh? Same element and same initial mass.
Yeah, so we could just use the same for number one.
No, yeah, part one is the same part.
Yeah.
Probably maybe the same decay constant to in the end. But you want to figure that out. Go ahead, work this out.
I don't think
Right, Ruel will do this one first. Right, so part one we can ignore it because it's the same thing as before. Right, but you can just practice it over, right? It's the same element, same initial mass. What was the number of nuclei we got? What's the number of nuclei we got for the last one? What's the number of nuclei we got for the first question that we did? And 17? Say 17, right?
Yeah.
Right. How we getting decay constant? We have a big problem here, no decay constant, because we are no half-life, right? So we can find half-life or we can do something else. What's the table? What's the table? Let's see. Got the? Arrow. So what else? Take. So you're trying to get the half-life, but you might just see the exact value there. The exact value there? No. Something else we can do. I'll give you a hint here. Look at the first one. Look at the first row. What does the first row give you?
So you can stress that.
A naught. Activity when time is 0. So if we have A naught is what?
A naught is equal to lambda by
N naught, right? So we can find lambda. A naught over N. Okay? Right, Jude? So you see a problem. If you had tried to divide it, you wouldn't have gotten an exact value. That's the problem. It's an option, but you're not really seeing that there. Wait, and I suspect you have a mistake on 3. What's that? What's happening from 3 to 4? Sorry, 2 to 3. It's increased. Yeah, probably have an error there. What do you get for lambda?
5.5 like that.
5.5 by 10 to the minus 4 s to the minus 1.
So
Right, work out the last 2 parts there. Right, work out half-life, activity after 8, and the number of nuclei after 8. Hurry up, I'm giving you 5 minutes. Last 3 parts add up half-life, decay, activity, and number of radioactivity.
So 1.26 by 33.
You got half-life already? Half-life is ln 2 and lambda. What you got?
1.26 by 30.
10 to the 3. Right? Then you find the activity after 8 hours. What formula you using here? A is equal to, how we get the activity here after 8 hours? A is equal to A naught. And T must be in. And part 5.
It's minus.
Yes.
So,
So you have 2 options, right? You can use N is equal to, or you can use A is equal to.
minus.
Okay, fine. And this is how much present. You can know how much T is something. Was he half like for the last question? So the first one that we did, what was it the key concept?
T constant 5.66 meters.
5 clicks, similar.
So you have 120.
Great, yes now. What we got for the activity? I guess the activity by 10 to the 6. Yeah. And then you can solve N, right? What you got for N? 1.39 by 10 to the 6, and you can divide it by lambda. Lambda is 5.5 by 10. Online, just make sure you get those same values, right? Killing, where you get A.
Now, another distance.
Come on, sit up there.
Say you get 2.5 by 10 to 10.
Right, so you can use A is equal to lambda N or N is equal to N naught minus lambda. Right, so try and do a little summary before you do questions, right? Do a quick revision, write down all the little formulae and put it up. I sent you the summary. You did this already?
It's not.
Not module 3.
I think so.
You got one of them. You got some big long one.
Yeah, so
Yeah, that module 3. Module 1 kind of. But when the summary small,
yeah.
I'll take and say, what's up? All right, so that's the end of module 3.
Nice.
Right, what we can do next week for the one before the exam, and then some energy other one. Right, but that's making this year you become full. Something. But message them first to make sure.
Yeah, one. Yeah, two.
Huh? Come back more. Well, come after